Here we are, the last example. So we're going to now approximate the lattice enthalpy for magnesium fluoride. And the first thing is to notice the charges. Magnesium is a second row element and it has a 2+ charge. We could also determine that from the proportion. So we have a 2+ charge for magnesium and a 1- charge for fluoride. Just as a reminder, the anions, you can find the charges by applying the formula group number -8. Alright, so we have 2+ and 1- for the charges of cation and anion. Let's take a look at the actual ionic radii of both. Okay, so magnesium 2+ is given right here, 0.86, and fluoride minus is 1.19. So we're going to add up both of those values. 0.86 plus 1.19 added together yields 2.05. So we're going to input that for the ionic radius, or the ionic bond length, R bond, into the equations. Alright, and then we count the number of ions. There's 1 magnesium, there is 2 fluorides, so that's a total of 3 ions. And of course, we need to also look at the Madelung constant for this. So it is 3 ions, so the value of N is 3. Now let's take a look at the Madelung constant. For this, we don't actually have a specific structure on the table of Madelung constant, so we're going to have to rely on the ionic ratios, the ionic radii ratios to determine this. Specifically, cation to anion. The cationic radius is 0.86 angstroms, the anionic one is 1.19. If we carry on that division, or that ratio, we find out that the value is 0.723. Okay, so let's take a look at the table, 0.723. First of all, we're dealing with magnesium and 2 fluorides, so the ratio is 1 to 2. So don't make the mistake of looking at this set of numbers. This is a 1-to-1 stoichiometry. The 0.729 falls in between the middle ones. That's why I highlighted the 0.414 to 0.732 in yellow. But you do not want to use the 1-to-1 stoichiometry because magnesium chloride does not have a 1-to-1 ratio. In fact, it has a 1-to-2 ratio. So you actually want to use the numbers right here. So the structure that it will most likely assemble or reassemble will be the rutile structure. So the Madelung constant should be 2.408 and not 1.74756. Right, so that's the one we want to stick with. So keep in mind the stoichiometry of your salt along with the value of the cationic to anionic ratio. Alright, so M is going to be 2.408, so we just need to input that into the equation. And at this point, we carry the calculation. So as I said in the previous example, take care of the last parenthesis first. Divide 0.3 by 2.05, press enter. Subtract that answer from 1, press enter. Then start the multiplications. Multiply your answer by 1389, press enter. Multiply that answer by 2.408, press enter. Multiply by -2, press enter. Divide by 2.05, press enter. Multiply by 2, press enter. Divide by 3, press enter, and you'll get your answer. Here I'm going to just show you the truncated version of all of that, namely that left and right parentheses have positive numbers. The middle parenthesis, however, will always have to yield a negative number, and that's why it's important that you input the charge with its actual negative and positive sign in it. Because at the end, when you calculate all this, you'll end up finding out a lattice enthalpy with a negative value. In this case, negative 1857 kilojoules per mole. Alright, now with that being said, this is the last example for lecture 19. Sections 5 and 6 of this lecture, needless to say, are the most convoluted and complex portions of the lecture. But hopefully, at this point, you've had some time to digest the information of enthalpy, specifically Hess's law and enthalpies of formation, so that this is not too bad. But it will be a good idea for you to practice drawing the Born-Haber cycles for pretty much any salt. Pick any salt that you want and try to draw the cycle. You don't necessarily need to have the actual values, but draw the cycle, show me the equations, and then I can tell you if you're doing this correctly or not. And of course, practice the approximation and see if you get, semi-close values to the correct ones, you could actually look up the enthalpy, the lattice enthalpies for pretty much any salt online. And if you apply the approximation, you should get values that are roughly in the vicinity. They might not be exact or super close, but they should be roughly in the vicinity of the true values. All right, so this concludes lecture 19. I'll see you on the next set of videos. Okay, bye-bye.